We're going to look at 11.2. There's a fair amount in it. We're going to look at convergence and divergence of series, and we're going to introduce you to some of the tests that we use. I believe off the top of my head that there's 9 different tests. That's 9 different tests that you use to see if a particular series converges or diverges. And so if you think about that, that's a lot of different situations. So why do we need so many tests? It's because there's so many different kinds of series out there. And for particular types of series, there's very often a test associated with it. So let's jump right in, no particular order. Let's look at what's called the geometric series test. Basically, if you have a geometric series, which I'm now going to call GS, suppose you've got a geometric series, sigma n equals 1 to infinity AR to the n minus 1. That's the generic version of what all geometric series look like. And the test says this: if the absolute value of R, the common ratio, is less than 1, the series converges. And if the absolute value of R is greater than or equal to 1, then the series diverges. And we also get an added benefit that we even know what the series adds up to. The series will add up to A over 1 minus R. So that's our first formal test. The geometric series test, only used on geometric series. I'm going to stop this for a second. Got someone coming in. Oops, this. Okay, should be good. So, this is our first formal test, geometric series test. So let's look at its application. You could get your geometric series written down like that. So first thing is you've got to be able to recognize what does a geometric series look like. It tends to, but not always, it tends to have a single digit, single number, followed by a fraction to the power of n, to the power of n minus 1, to the power of n plus 1. Doesn't really matter, they're all geometric series. When you see a series that has this particular shape to it, then recognize it's a geometric series. Then you have to find what the R value would be in this question. The R value is pretty easy to get. It's that fraction there. So you find the R value. You then apply your test. Is the absolute value of this guy less than 1? Well, let's find out. Yes. So you can say, by the geometric series test, the series converges. Now, though you do not get in homework boxes to write sentences, will you imagine that you always write them down? Because in written work and written proofs, that would be expected. What you tell people is the gist of what you've done. I'm telling you what test I am applying to this series. It's a geometric series test. When there is 9 tests, you see, you have to tell people which one you're using, or else they don't know why you decided it converges. You could have just flipped a coin in the air, and if it lands heads, you're going to say converge, right? So you need to do that. And then, very often, at least in this thing, they say at the bottom, if it does converge, find its sum. Well, the sum of a geometric series is what you would get if you add it all up. Now, to be able to do the sum, we need to know two things. We need to know A, the first term, and we need to know R, the common ratio. Well, we already know the common ratio, right? It's 4/5. Now you might think, yeah, but that's got n and it should have n minus 1. Isn't that going to make this, you know, I don't know, 4/5 squared, or is it going to make R different? The nice news is that R is that. It doesn't matter what the power is. You can do some algebra to it to make it look like this. That doesn't matter. On the other hand, A is not necessarily 3. In fact, the only time A will be 3 is when this power here is n minus 1. A is basically the first term. So if we start with n equals 1, A is going to be 3 times 4/5, in this particular question to power of 1, that makes A 12/5. So very often A is not obvious. I think R is obvious. A typically needs a calculation. Right, this horrible mess here becomes 12/5 over 1/5, and we get a nice answer that it's 12. So that is essentially a bread and butter typical geometric series test where you're given the formula. You okay with that? Are we happy with that process? See if I can see some of your faces, or nods or something. Again, nods. Nods is good. Oh, and thumbs up and everything. Right. Well, sometimes you get a geometric series not written in its sigma notation, but written something like this. Yes, Travis, what's your question?
By definition, a series is infinite, right?
A series is what you get when you add up an infinite sequence. So by definition, a series is either a single number, 12, or it's divergent.
Okay, but
so it's made up of an infinite number of things being added together. But technically, the series itself is the result of adding all those terms. So technically, a series is a single object. It's 12, or it's infinite, or it diverges.
Okay.
Right. I don't know if that's been a bit lawyerist, but that's what it is. Right. This is a geometric series. This is easier to see in my brain because it has a shape to it that I recognize as what geometric series look like when you write them in sigma notation. This is not clear that it's a geometric series, yet it is. So I guess you might ask, how do you tell? Well, for a geometric series, don't you start with any number in the universe you like? That's not the problem. Isn't it once you start with a number, you continually multiply by the same amount each time? Now, it doesn't mean that it has to be a number like times 3 times 3 times 3. They're actually a little bit easier to recognize just because your brain works better that way. Would you agree in this case, you multiply by -1/4. Then to get to here, you multiply that by -1/4. Then to get to here, it's -1/4. And then get to this one, it's -1/4. Can you see that once you start with 4, to get all consecutive terms, don't you just multiply this one or the previous one by -1/4? Which makes it a geometric series. It also makes it that R is -1/4. It's called the common ratio, right? The number that you multiply throughout a geometric series, right? The thing you multiply to get the next term to get the next term. That's called the common ratio. In this case, it's -1/4. If you stick an absolute value around it, Would you agree that that is less than 1? So this guy converges. Now, they very often have as a part B, and if it does converge, what does it converge to? So in this case, A over 1 minus R. Now, I've got R. Be careful. Isn't R negative a quarter? It may have lost its negativity in the test, but isn't R still negative a quarter? Do you see how that bottom's not going to be 3/4? That bottom term's going to be 5/4. Now, slightly easier, in fact, is A. Won't A in this structure be the first term? In this case, 4. You know, over here we had to do a little calculation to figure out who it is. Here, it kind of is given to you on a plane. And at last, I finally got an answer that is a fraction. Are we cool? Okay, we're good. I think I should do for one last one a diverger, right? Because both those ones converge. So, top of my head, diverger. Now, there are a couple of things that kind of tell me right now that that's going to diverge. It happens to be a geometric series, agreed. Would you also agree that this particular series just gets bigger and bigger and bigger?
Yep.
So can you imagine you started adding all the infinite terms that were there? Is it kind of intuitively obvious that the answer should be infinite? Right. But for the sake of testing, geometric series, R in this case would be what?
3.
Yep.
3.
And I don't care what A is, because the absolute value of that is greater than 1, well, equal to 1 also counts. It's going to diverge. And divergence is basically the end of the series, and I've broken my own rule by the geometric series. The series diverges. Are we cool with that, guy?
Yeah.
I'll show you a cool little side issue. I'm going to use geometric series to find the fraction that represents any given repeating decimal. Right. Now, since Abby has just woken up, I'm going to pick and put Abby. So, 0 point. Give me any 3 digits you like for a repeating decimal, Abby.
582.
So can you imagine the repeating decimal 0.582? Agreed? Now I'm going to turn that into a geometric series. So it's going to go 0.582. Then I'm going to add 0.3 zeros 582. Then I'm going to go 0.6 zeros 582. Would you agree that this series would generate that repeating decimal? You know,
Yes.
if you can, yeah. Now, it is a geometric series. A is 0.582. What's the common ratio? Well, it's a horrible decimal, isn't it? I believe it's 0.00. Do I need 2 or 3 ones here? 1 0, 2 zeros. I need 3. Would you agree that that is definitely less than 1 and so it converges? And according to the geometric series test, it converges to that guy. Oops. It converges to that guy, who happens to be and if you multiply top and bottom, you get that. So that guy should give you the repeating decimal that you were just given. What you could probably do, I'm not saying it's going to happen in this one, but it could. Well, I think it does. 194 over 333. You would simplify it down and you get that guy. And now, to confuse you. Confusion is not normally a good thing to do to students, but there is a reason I want to confuse you. .9 repair is 0.99999 forever. Great. Would you agree that's a geometric series?
Yes.
It would start with the 0.9, and then you would add a 0.09, and then you would add another one for eternity. The R value is 0.1, the A is 0.9, and therefore its sum should be A over 1 minus R, which is 0.9 over 0.9, which equals 1. Now, the Greeks never had this problem, but if the Greeks ever discovered this problem, I'm pretty sure a couple of them, their head would explode. This repeating decimal is 1. It's the problem with our concept of infinity. You could say, quite reasonably, but it isn't 1. It's 0.99999 to the end of the universe. And I could say, okay, but 0.99 to the end of the universe has the same limit. It's 1. Well, let's turn it on its head. What would you get if you took 1 and subtracted 0.9 repair?
0.1. Wait.
No, wait, you wouldn't. Oh, 0.01. Oh, no, wait. 0.2 million years go by. 1. Oh, wait, there's still some room. There's still some more places to go. Wouldn't you have to go to the end of the universe? Right, at infinity? But there is no stopping point of infinity. So what does this tell us? It tells us we have to be really careful and realize that limits are not the same as exact values. The limit of this is 1, right? I guess its exact value is 0.9 repeater. They are conceptually meeting at the same place, but the limit of something doesn't necessarily mean it is a. We don't say really, or at least we shouldn't say, that the sum of a geometric series is 3/4, is 1. What we really should be saying is the limit of a geometric series is 1, or whatever, 3/4. So, just to prove a point that these are limits of things, not necessarily the exact value. So remember the poor frog that jumps 2, then 1, then a half a foot, then a quarter? If the question was, does that frog reach the well? The answer is that the limit of its series is 2, but the frog technically doesn't reach the well. Which sounds like a contradiction, but it's not, right? The limit can be 2, but the jumping process always has a little bit further to go, doesn't it? Okay, that is our first guy out the way. Next guy is going to be called the divergence test. Before we even get started, this test only proves that certain tests diverge. Shouting at you. It doesn't prove that they converge. See, in the geometric series test, doesn't it tell you when things converge, and it also tells you when things diverge, right? It tells you both sides of the coin. A divergence test only proves that certain tests diverge. It doesn't prove that they converge. And it doesn't prove that because there are series that diverge, but the divergence test doesn't catch them, right? It's a bit like it's not a very strong test, right? It catches the blatant ones, but it misses some of the subtle ones. So there are some series out there that you won't be able to prove that they diverge by using this, but they still diverge. So let's show you what that looks like. If you take the generic series that looks like this, if the limit as n tends to infinity of an equals L, and L is not 0, then the series diverges. Yeah. So, what might that look like? There's a series. I could certainly write down the first few terms, but I don't think it would help with pretty ugly fractions. Kind of hard to see what's going on. The question is, use the divergence test. Does this diverge? That's all I'll be able to tell. Well, if you take the limit as n tends to infinity of 2n plus 1 over n plus 3, I got a couple of strategies for this. Could I do L'Hopital on it? It's pretty easy to do L'Hopital, would you agree? Could I divide the top and bottom by n, get it that way? Yeah, that works too. Any particular preference for which method I'm going to use? Do you want to see L'Hopital, or do you want to see you divide top and bottom by n?
LHOP.
Okay, stick an L there. You're now going to get the limit as n tends to infinity of 2 over 1. There's your answer, 2. Is that number not 0? Right? In other words, is it any other number? And the answer is yep. So, by divergence test, the series diverges. So if this thing has a limit, and well, they all have a limit, but if this thing has a limit that's not 0, it diverges. Pretty simple test, right? Can you kind of understand why that would make sense? If all of these terms eventually level off so that they're indistinguishable from the number 2, can you imagine you're going to reach a point in the series where you basically just go 2 plus another 2 plus another 2 plus another 2, you know, to infinity? Can you see why that would add up to an infinite total, and that's why it eventually diverges? Diverging questions are very nice because that's typically the end of the question. There isn't really any point in finding out what S is equal to. Because I know. It's infinite, isn't it? But nobody's going to ask you that. Normally when it's diverges, they leave it that way. How about this fella? If I tried the divergence test on it, I get the answer 0. And unfortunately, some people say, if it's a number, it diverges, and if it's 0, it converges. That is not stated here. If L, I guess I should write it down maybe. If L equals 0, we know nothing. The series might converge, the series might diverge, we know nothing. Don't normally write that down. So this doesn't mean that that particular guy does it. In fact, do you recognize this as one of the harmonic series? So, no good. Are we good? Right, let's put in some weird ones. Imagine I added up all the cosines in the world, right? Cosine 1 plus cosine 2 plus cosine 49 plus cosine whatever. What's the limit as n tends to infinity of cosine n?
It
Has
like
no fix. Say again?
it kind of like oscillates, right?
Yeah, so it doesn't have a limit, right? So what's the answer to this question? Well, the answer to this question is we don't know. If it had a limit of 5, I'd say it diverges. If a limit is 0, I'd say I don't know. If I don't know what its limit is or it doesn't have a limit, we don't know. These buggers are the hardest series in the world to find out if they converge or not. They are not pretty. So you'll be glad to know you don't get any of them. The only ones they're going to give you are ones that are doable, right? Ones that are convergent or ones that are divergent. How about this? There's my harmonic guy. Oh, let's stick a 10 in the top. And this guy. Okay. Basically, you would split this thing into 2 pieces. Without getting into too much detail, would you agree this is a geometric series and it converges? I'm not going to prove it, but it converges. Would you agree this is basically just the harmonic series, but instead of 1 plus a half plus a third, it's 10 plus 10 halves plus 10 thirds plus 10 quarters. If 1 over n diverges, won't 10 over n diverge? So anybody that's in the harmonic family basically diverges. So this diverges. So here's your problem. If you have a series made up of 2 terms, and one of the 2 terms diverges, and the other one converges, what would the conclusion have to be about the original series, in this case, this guy?
It diverges.
Correct. This converges. Let's pretend this converges to 5. Would you agree infinity plus 5 is still 5, and it's still infinity? Right. So if you have a series that's made up of 2 distinct pieces, and one of them converges and the other diverges, your conclusion will be it diverges. Different world. Suppose we have that guy and that guy. Do you recognize both of these are very simple geometric? Wouldn't R be a half converges? Wouldn't R be 3/4 converges? Agreed? So you find each piece separately and you prove to me that they converge. Shouldn't you also individually find what they add up to and then add the two answers? Don't say R is a half, R is 3/4, and combine them into one big R. That's not how this works. R is a half, get the answer. R is 3/4, get the answer. The two answers combined is what the series would eventually add up to. Are we good? Right, I want to give you some really weird ones. Oh, n to the power of 1 over n. Another way of writing that, isn't it the nth root of n? I am going to tell you this answer, and it's magic. You just remember it, because I'm telling you that's what it is. Anyone want to have a guess before I just say this is what it is, and trust me? What's your gut feeling for what that might become?
Maybe 1?
Good gut feeling, yes. Second and final weird one. If you ever see some weird fraction that looks like this, you're going to be using the divergence test on it. This one, I'd probably, if you know, I can't remember the first time I saw, so I'm winding back here. Believe it or not, there was a time in my career where I didn't know what that was because I hadn't met it before, and then it appears and I got the answer. That might be true for some of you today. That might have been the first time you've ever looked at what the limit of n to the power of an nth is, and it's 1. And I'm pretty sure that when that happened, I'd probably have guessed 1 as well. My second backup guess would have been 0. Right? But 1 is the one I'm going for. This fella here, I actually do have vague recollections of it. And when I saw it, it was not intuitive to me. This guy is equal to something. Do you know what he is equal to? And if you guess this, you are much better man than I am. Because I remember being told this version of this and I'm thinking, nah, that can't be true. And it is. And actually, if we have time when we do Taylor's series, I'll prove it to you. But until now, we'll just have to trust it. Any gut feelings?
2?
Oh, interesting. Would you believe it's e to the power of 6?
Yes.
God, you're much more trusting than me. I just went, I'm sure. I went, what? Where did that E come from? I think I could figure out where the 6 came from, but where did that E come from? Right? In general, 1 plus a over n to the power of b over n, its limit as n tends to infinity is e to the power of ab. And you just have to trust me. So back to this series. Since that limit is 1, doesn't that diverge? Since this limit is what, e to the 6, doesn't it diverge? So doesn't that mean if you ever see a series with one of these guys in it, right, isn't the series going to diverge? And the divergence test will do it. You will simply just write that down as if it was obvious, and then by the divergence theories, by the divergence test, the series diverges. If you see a series like this, you're just going to do that, and then you're going to finish with, by the divergence test, it diverges. There we go. So that is some examples of what's called the divergence test. Let's look at our next one, which is going to be the harmonic series. This really isn't called a test, but we can use it. The mother of all harmonic series is this guy. And we know, because I tell you, that it diverges, right? So if you were going to prove it, you would just say, it's a member of the harmonic series, therefore it diverges. Because every single member of the harmonic series diverges. Even, as long as the terms are positive. So how about this fella? Doesn't this guy look like he might have a chance of adding up to a number like 2? Remember, 1 plus a half plus a quarter. Yet when you can see its formula, you can see it's a member of the harmonic series. If you pull out a common factor of a half, can you see the harmonic series a little bit better? So if you ever see a guy that looks like this, or looks like this, or looks like, I don't know, this, which would basically just be actually, that one would be quite heavily disguised. Do you see when you round it off, this one looks sort of a kind of geometric, doesn't it? And harmonic series, the terms do get smaller, but the series is still infinite when you add it. How could I check that that wasn't a geometric and actually was, in this case, a harmonic? Well, wouldn't you just do consecutive terms? Right. To get from 10 to a half, don't you multiply by a half? Right. What do you multiply to get from 5 to 10 thirds? You multiply by 2 thirds. Do you see how that was a half, but this is 2 thirds? It's not a geometric thing, right? Shouldn't it be times a half, or times 2 thirds, times 2 thirds? There's not a lot in harmonic. If you recognize a series has a harmonic in it, it diverges. It doesn't matter if they stick a 2 thirds to the n as well. Remember the rule, if one bit diverges and the other bit converges, the whole thing still diverges, right? So if any series contains a member of the harmonic series in it, you're just going to know that it diverges, and your sentence would be, it's in the family of the harmonic series, so it diverges. So that was a pretty quick one, right? Because there's not that many things you can do to a harmonic, right? You can double or treble the bottoms, or you can stick a 4 on the top, right? There's not too many things you can do to it. So there's one last guy, and that's 11-2 finished. I'm calling it a telescoping series test, but it's a bit like saying the harmonic series test. They're strictly speaking not tests, but they do allow us to find out if things converge or not. Let's show you what one looks like. But what does a telescoping series look like? Well, it typically has this format. It will be made up of two terms, because that's the entire series, subtracted, right? And the two terms will be very closely related to each other. So let's see if this one converges or diverges. If you plug in 1, you get the log of 2, take away the log of 1. Agreed? That's the first term. Now, instead of writing them this way, I'm going to write them down the way. So then you'd add the log of 3, take away the log of 2. And then you would add the next term, which would be the log of 4, take away the log of 3. And technically speaking, couldn't you keep doing that to infinity? So let's suppose that we stop. Oops. Let's suppose we stop at the generic point here, right? Where n is allowed to be any number in the universe you like, right? So it's just an arbitrary stopping point. Can we simplify all of this? Well, yes is the answer. So here goes. Won't that 2 get killed off by that 2? Won't this 3 get killed off by this 3? Won't this 4 get killed off by a guy that I would have written there? Wouldn't there be a guy here that would kill off the guy that's there? You see there's this kill thing going on, right? So what would this equal? Well, it would equal that guy take away the natural log of 1. Wouldn't they be the only two terms that would make it out alive? And then you say, oh, but it doesn't really stop anywhere because n is infinite. Well, if you plug infinity in here, isn't the log of infinity infinity? Take away the log of 1, which is 0. Would you agree infinity take away 0 is still infinity, so this guy diverges. Do you like the logic behind how I proved that that particular telescoping series diverged? Does it intuitively kind of make sense as an argument? Now, do another one. Suppose I have n equals 1 to infinity, and I have this guy, take away that guy, right? You should be able to recognize the shape of a telescoping series. Don't they typically have two guys subtracted and the two guys look similar, right? Two logs subtracted, two fractions with a 2n in them being subtracted. That is what a telescoping series look like. If this was a plus, that wouldn't be a telescoping series. It probably doesn't have a name, but it wouldn't be telescoping. And what I just did here would not work. So let's do the logic. If you plug in 1, you get a third, take away 1. Then the next guy you get is a fifth, take away a third. Then you get a seventh, take away a fifth. And then you get a 1 over 2n plus 1, take away a 1 over 2n minus 1, right? Let's see what happens. Won't this guy get killed off by him? Won't this guy get killed off by him? Won't this guy get killed off by a guy you can't see? Won't this guy get killed off by a guy you can't see? Who's left? This fella minus that guy. Agreed? Now, what will that equal when you go to infinity, right? If you kept on doing it, right, forever, what would happen to this term?
It would go to 0.
So here is a converging one. And we even know that it converges to -1. And you might think, why does it converge to -1? Do you notice that the first term is -1? And doesn't the way this work, everything after it basically kills ourselves off. So you've just got one term at the start that lives, and all the other terms that come after it will eventually be killed by another term that comes after that. And as that happens, don't the terms get smaller and smaller and disappear? So the argument there is that in a telescoping series, if you go through this process, you can get some that diverge, right, like this one, and some that converge, like this one. So if you're a telescoping series, then shouldn't you be able to tell which side of the fence you fall on, the converging side? In which case you'll always be able to figure out what it converges to. Or is it a diverging one? In which case that's the end of the question. Well, that would be good. And for the majority of the questions, that's fine. But sometimes it doesn't look like a telescoping series, but it is. That does not look like a telescoping series, does it? Doesn't help much. Still doesn't look like a telescoping series. It kind of looks like it's harmonic series, but that term there stops it being harmonic, right? A harmonic would be that, right? And in fact, wouldn't 1 over n plus 1 count as a harmonic as well? But this isn't, that's that. So we are going to have to do a piece of algebra that you had to use in Calc 2. And the thing is called partial fractions. I say this quite a lot in a calc class. Every single, without exception, thing that you've learnt up to this point, even if it was in Math 94, which is way, way back in the day, every single thing that you have learnt can and will eventually reappear in your math, no matter how far up the food chain you go, right? Calc 4 or beyond. You are going to have to use some stuff. Does anybody even remember partial fractions? One person remembers partial fractions. At least one person has put a thumbs up that they remember it. So can you imagine what's going to happen? A couple of people that's come back to them, right? Can you imagine that what's going to happen in this question is, if I don't know how to do partial fractions, there's no way I can continue. So you're going to have to go and watch a YouTube video on how to do partial fractions. And I'm going to show you a really cool technique that you may have been shown. It's called the cover-up method. Have you ever seen the cover-up method for partial fractions? Right, you're about to get your mind blown here. This is major magic. But what it does that's really cool is it gets you the answer to A and B almost instantaneously. Otherwise, you're going to have to do the general algebraic method, which is you put them back together as a fraction, and then depends on you get taught by. Sometimes you do a technique that is you match the coefficients, and sometimes you do a technique where you choose n is 1 and n is 0, and you eventually solve a system of equations, and that system of equations eventually gets you A and B. In other words, 10 minutes work. And I'm going to show you, maybe pushing it, 10 seconds work. So if I can sell this to you, great. If what I'm about to do makes no sense at all, then you'll just do it the good old-fashioned way, and I'm cool with that too. So here goes. I think we all agree that that bit's easy, right? There's a number above the n, there's a number above the n plus 1. So, the number that goes above here, what we call a, right? This number here, right? Go over here and cover up the n. You see the little fraction called 1 over n plus 1? What value of n makes n 0? The answer is 0 makes n 0. Plug 0 in here. 1 over 1 gets you 1. Okay, the number that goes above n plus 1. Cover up n plus 1. What value of n makes n plus 1 equal to 0? Negative 1. Plug in negative 1 here, the answer you get is negative 1. There's your partial fraction. Cool.
Quick question: does this method only work for like first degree, or will it
Yeah,
work for
only works
polynomials?
for, nah, only works for linear.
Okay,
But you're only going to see linear, so don't worry about it in this section, right? So it works for the ones you're going to see. We cool? Right, let's try a hard one. Typically, these can be different, but because we're only going to do it for telescoping series, they're going to look something more like this, but that doesn't really matter. They're going to be a 2n plus 1, right? And a 2n minus 1. So here goes. The number that goes in the top here, right? The 2n plus 1. You cover up 2n plus 1. What value of n makes 2n plus 1 0? A half or negative a half? Which is it? Because I see mouthing and it looked like a half, but I'm wanting you to be sure that it's not a half. Isn't it negative a half? Okay, so that's what you're saying. Negative a half in here. Negative a half is negative 2. 4 of negative 2. You get negative 2 there. If you want the guy that goes here, 2n plus 2n minus 1, don't you cover up the 2n minus 1? Would you agree in this case it's a half that makes that 0? A half here goes 1. 1 plus 1 is 2. 4 over 2 is 2. There's your guy. So you could, if you're really good at it, I think you could do that in 10 seconds instead of 10 minutes. Would you agree if you're fast? Now, it's total magic. I'm making no qualms about that. To me, magic is something that I tell you works and it's cool, but there's no intuitive reason why it should work. It does have good math foundations behind it, right? So it does have, you know, it can be proved that this technique works, but I don't think we want to spend, 20 minutes proving that it works. Are we comfortable with, yes, it works? Now, back to our guy. Remember this fella? Him? With the sigma on it. Let's put in, well, if you put in 1, you get 1 over 1, take away a half, then you get a half, take away a third, then you get a third, take away a quarter, then you get 1 over n, take away 1 over n plus 1. Do you see it cancels this direction? That gets killed by that. This gets killed by that. That gets killed by a guy you can't see. Won't that get killed by a guy up here you can't see? So in this case, you are left with 1, take away that guy. But doesn't that become 0? And so it converges. And when you have a telescoping series, don't you get as an added bonus, at the same time you're proving it converges, don't you get to know what number it converges to? So you get 2 for the price of 1 for that one. If this was the guy I was doing, right? Suppose this was the sigma, right, over here. You plug in 1, what you would get? You get negative 2 over 3 plus 2 over 1. Then you'd get negative 2 over 5 plus 2 over 3 then you get negative 2 over 7 plus 2 over 5, then you got a whole load of guys, and then you put this fella in. And would you agree? Let's see how the cancelling goes this way. They two cancel. These two cancel. Won't this cancel with a guy that you can't see? Which of these two guys gets cancelled? Does this one get killed off, or does this one get killed off? The left or the right? These two cancel. These two cancel. These two cancel. Which one would be killed?
The right.
And so we would be left with a negative 2 over n plus 1 and a 2. And would you agree that goes to 0, and that's 2, so it converges. And it converges to 2. That cool? So when you're looking at these telescoping series, if they're nice to you, they'll write them like this. I mean, if they're really nice to you, won't they write it like this? But they're more likely to give you that version. And if they're really nasty to you, won't they give you this version? Which you have to turn into that version, which then has to be turned into this version before you can even do the damn question, right? Right. Is there any questions about that? Because if we're going to look at some of the homework, just scan through it, make sure I've covered everything, then we can get started on our next section, which is 11 to, I should say. Are we comfortable then about geometric series, divergence test, harmonic series, guys, and telescoping series, guys? Right, so we've got 4 guys already, and only 2 of them counts towards the 9 total that I gave you. Well, let's have a look at what that would look like in the context. Oh, I got a chat. Somebody said something. I'm going to share this. James, you put a comment in the thing here that you remember it and it was a pain. And it took forever. What I didn't get from your note is, have any of you seen the cover-up method? Was this like, where in heck did that come from? Or where were you in my life when I needed you, right?
Never seen it, but just when you think it, at least when I think about it, I can kind of see in my head how algebraically it would work, and it just kind of makes sense. That's why I was asking if you could do that for, nth degree polynomials.
I wish it was true.
Ones.
Yeah, unfortunately, no. You have to do the general algebraic method. But the plus is that the only ones you're likely to see are the linear, right? Okay, so let's zoom in and check our homework. Okay, so hopefully right now you're all seeing what your homework looks like. Okay, I'll just randomly pick question 2. Oh, they're being too nice to you, really, but that's fine. Haven't they told you it's a geometric series? I was hoping I could say, can you tell by looking that this is a geometric series? That would have been a better form. But since it is, that's fine. But if you look really carefully, isn't there a kind of feature in geometric series that if you start with something, it's a constant multiplication? The thing is that the multiplication is not always obvious, agreed? So how do I find out what R is in this question here? Well, the simplest thing to do is take the second term, which is -6, and divide it by the first term, which is 5, and that'll be your R value. So -6/5 is the answer. Now, isn't the absolute value of -6/5 bigger than 1? So your answer to that question would simply be that. Now, the homework doesn't give you the features where you would be writing down all the things that I did, but will you try not to get into taking too many shortcuts, because I want you to be good at math when you go to university and you do a test. And I don't want you to just say, it's divergent. And then the guy says, well, prove it to me. And you say, well, I can't remember how you proved that. I just remember that it's divergent. That's not good math. If you were doing this one, would you agree, since it's geometric, wouldn't it be 8/9, which is a converger? But then wouldn't you do the A over 1 minus R thing here? When the questions are written in this format, isn't A easy? It's 9. And won't you have already figured out who R is before you got to that part? So you've pretty much got everything you need. There's a geometric series. There's a geometric series. Right, here's one written in sigma notation. What is the R value?
0.64.
So it converges, doesn't it? Have you noticed that if it's geometric, pretty much you can tell like that, boom, it's going to work, or not, in this case may be. Right, question 7 is a geometric series. I think your problem is going to be telling me who R is. And I think part of that is the way it's written. Does anybody know what R is in question 7?
1 over pi.
Nailed it. Do you know a better way of writing that would have been 5 times, in brackets, 1 over pi at the end. Can you see the R value a little bit clearer now? You could wrongly see the pi at the end and think pi was R. But I mean, the big picture isn't the R value 1 over pi. Now, once you've figured that out, it's pretty much good to go, isn't it? If I wanted to find A here, wouldn't I have to plug 1 in? In which case, what would that be? A would be 5 over pi, and R would be 1 over pi. Do you see that series in front of you in question 8? Let me rephrase that differently. Do you recognize what kind of series it is? That's a better question.
Harmonic?
Yeah. Isn't it 1 over 3n? So if you could suck out, well, not 1 over 3n, sorry, 1 over 7n. My brain was thinking you could pull it out, but 1 over 7n, right? It's harmonic. So you can pick it diverges, because if you're in the harmonic series and you're all positives, right, aren't you guaranteed to be a diverger? Because all of them are, right? All positive harmonics are. So you just type in the word diverges. Question 9, converges or diverges?
Diverges.
Agreed? Prove it to me.
So I ended up going on the limit of, my question was a little different. It was plus
Okay, yeah.
9. But anyway, taking the limit of it, going through, I ended up factoring the k's out, and then that left me with taking the limit of k squared over k squared times 1 minus 4 over k plus 9 over k squared.
Mm-hmm.
And then when you end up substituting in your limit of k, that ended up coming out to be 1.
Yeah.
And then 1 is not
that's
equal
perfect.
to 0.
Yeah. Essentially, you did the divergence test. You might not have known that that's what it was called, but that's what you were doing. Do you know, I would have just taken, just notice, do you notice sometimes they use n equals 1 and sometimes they use k equals 1? I'm sure we've mentioned that. It's totally makes no difference. I would probably just look at this as a big picture. Would you agree that if you find the limit of that using L'Hopital, the answer's 1? And can you find the limit of this by divided by k-squared, which is essentially what I think you were doing, and you get the limit 1. So if it ain't 0, it diverges, right? That's called the divergence test. What do you think would happen in 10? What's the limit of 1 over 2 plus e to the negative n? Just brute force it. Don't try to hop it all.
1/2.
Yeah. Won't e to the minus infinity just be 0? And 1 over 2 plus 0 is a half. And that makes it a diverger. Because in the divergence test, if the limit ain't 0, it diverges. If the limit is 0, you know nothing, go look for some other test. This guy could be split apart and be made into something that looks like a telescoping, but don't. Couldn't you just find the limit of what's inside the logs? Would you agree that that eventually becomes a quarter? And so won't the full limit be the log of a quarter? And isn't the log of a quarter not 0, so by the divergence test? So that's a diverger. There's a guy made up of 2 pieces. Hopefully you recognize 1 over n, and you'll be able to come up with the answer. That's a good question, 13. Converge or diverge? It's a one-off. You've got to figure out how to do it. So it's not a telescoping, and it's not a geometric, it's not a harmonic, it's something else, you know. It's divergence.
I ended up doing L'Hopital's 3 or 4 times on that.
4 times, yeah. And you got the answer in infinity?
Yep.
So it diverges. In fact, not only does it diverge, you could say, heck, it diverges, right? You know, if you add up, if your limit is a half, you diverge. Imagine your limit was infinite. I mean, that's like overkill, isn't it? Even the sequence diverges, so you've got no chance of anything else happening. Right, so who is our first telescoping series? They are too nice to you. You see it there? Now, do you see this thing that they're calling SN? Remember when I wrote down all the terms and I finished the N? That was SN. That's essentially what that was. So can you imagine you're going to have to split this up into 8 over n plus 1, n minus 1? Then do the partial fraction thing, then do that whole kill, 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 kill thing, and it will converge to something. I haven't done one like 19, so let me do 19 for you. 15, I should say. Oh, we got a comment. What was that one? Okay, I've lost the darn thing. Here we go. This may not be the same question, but you know that they keep, you know, when you get your homework, they do variations on a theme anyway, so this is basically the question I'm talking about. If you take this fella here, isn't the log of 2 things divided the same thing as that, right? For ease of calculation, can we just forget about the 9? If it's going to diverge, won't 9 times infinity still be infinite and it's still going to diverge? And won't be 9 times a half still be a number, and it'll still diverge, right? So we kind of know where that's going. And if it converges, then, you know, 9 times a half is, you know, whatever, it works, right? So can you imagine plugging in 1? So you're going to get the log of 2, take away the log of 1. Then you're going to get the log of 3, take away the log of 2. And then basically, I'm getting SN here, which is what you get when you add up the first n terms, right? That's what they're calling SN, which is. Let's see which direction the deaths happen. Oh, they go this way, right? So won't that one kill this one, and that one will kill that one, and this guy gets killed by somebody you can't see. And it looks like we're going to be left with this fella. Take away that fella, right? Would you agree that's a diverger? Okay, so just a little bit of algebra and we were good to go. But I think we're pretty close to being done here. Can you see a partial fraction that you're going to have to do, and then it's a telescoping series. In this question here, isn't a over e to the n a geometric series? Wouldn't the r value be 1 over e, right?
Yes.
I think with, what was it, 5 over pi to the n was one that was earlier on that kind of looked like that. Do you recognize 5 over n plus 1? Can you see that that's going to be a telescoping series question? So this one's a big question. You're going to have to find out what the e over e to the n does, which I believe converges. And you're going to have to look at the 5 over n plus 1, which I believe converges. When you have to find, so the answer, 99.99 is going to be a converge. But don't you have to find the answer to each of these separately as a sum? So if this is 4 over e and that's a half, can you imagine you're going to write 4 over e plus a half as your answer? Right? So you're going to have two separate bits added. And just to finish, and then we can start our next section. Arctan 6n. What on earth does that guy get? Converges or diverges? And you're going to have to prove it to me.
Diverges, it should be about pi halves.
Oh, nailed it. Yep. First, the diverging part. I'm using the divergence test. Do you know arctan? I like to call it inverse tan. I hate the term arctan. Inverse tan of 6n. Can't you brute force it? Just put infinity in. Do you know the inverse tan of infinity is pi upon 2? By the divergence test, if the limit ain't 0, you diverge. In this case, the limit is pi upon 2, so you diverge. Which means diverge, which is kind of overkill, but I guess. I wonder if I can do this. Oh, good. Do you know that you can copy and paste diverges if you're lazy? And that would be the end of that. So, where are we off to now? Well, we're going to look at a new test. It's going to involve Calc 2, amongst other things. It's called the integral test. You will use the integral test when you've got a series that looks like you could integrate it. So if you see a series there, if the n's all turned into x's, it would be, oh, you know, I could integrate that with a u sub, or I could integrate that with a power rule, or I could integrate that with some kind of integration by parts, or whatever I could come up with, right? And then there's a good chance that that's a candidate for the integral test. Now, it starts off like this, as all of them do. Here is the generic series, right? Now, you have to think of a of n as being a function of n, right? So if a of n is n cubed over n squared, isn't it just f of n equals n cubed over n squared, right? So what the integral test says is, if f of x, so you turn that into a function of x, is positive, decreasing, and the integral from, say, 1 to infinity of f of dx exists, then so does the series, and it converges. The first part are the conditions for using the integral test. If those conditions are not met, you aren't allowed to do this. I mean, you could do it, but it won't give you any valid conclusions. The function has to be made up of positive terms, and it has to be decreasing, essentially, right? And if this exists, right, if this is a number, then it converges. If this diverges, basically, if this integral is infinite, pretty cool. So basically it says a series behaves in a very similar way to the function. And if the integral from 1 to infinity of the function is a finite number, the series converges, and if it's an infinite number, the series diverges. Pretty cool. Let's put it into action. One over n cubed. We know 1 over n doesn't make it, agreed? Because isn't 1 over n the harmonic series? But 1 over n squared and 1 over n cubed do not count as members of harmonic. Harmonic series are just 1 over n, or you double it, or you make it 2 over n, or you do it 1 over 2n, right? It's all linear, right? You just muck about with it in a multiple kind of way, right? You only multiply the bottom or top, right? That's the family of harmonic. But 1 over n squared and 1 over n cubes, nothing like that. So step 1 is look at the equivalent real valued function. Would you agree it's the same thing, or at least it behaves the same way as 1 over x cubed would? That seem reasonable? Right. Now, let's get the conditions. Would you agree, oh, by the way, in our world, isn't x going to be greater than or equal to 1 because of this guy here? Right. Would you agree that 1 over x cubed, i.e. f of x, would you agree it's just obviously positive if x is 1 or bigger? So that wasn't much of a check. How am I going to check it's decreasing? In a calculus kind of way.
Use a derivative test.
Okay. So if I call this guy x to the negative 3, won't its derivative be that guy, which becomes this guy? Would you agree that that again is pretty obviously negative as long as x is greater than or equal to 1? In fact, it's negative for any x, but definitely it's true for that. And the derivative test basically says if a derivative is negative, doesn't that make the original function as decreasing? So do you see, before I can even do the integral test, I have to check that the conditions for using it actually are true. If you gave me a series that was, I don't know, something like that, I couldn't use the integral test in that, because doesn't this go positive, then negative, then positive, then negative? Wouldn't it have at least half of its terms would be negative, and it would fail under this condition, right? Agreed? Now, what about why do you have a decreasing one? Well, just trust me. it has to be decreasing or the test isn't valid. So now we're left with the last piece of the puzzle. Every single piece of thing that you have ever learnt is going to come up and bite in the bum. Today we've had to learn how to do partial fractions. That's been a while. Can you remember from Calc 2 how you go about finding infinite limits, right? They're called indefinite, improper integrals type 1. What do you do? I know what to do. Do you know what to do? Last chance. You find the limit. You can pick any of the letter of the alphabet. Did you pick t tends to infinity or n tends to infinity? Can you remember?
We
I
use
think it
T.
was T.
Okay, so we'll do t tends to infinity. The integral from 1 to t of, do you notice I've turned the 1 over x cubed into a negative power to make it easier to integrate? So what does that get me? It gets me the limit as t tends to infinity of this guy. Well, add 1 to its power, divide by the new power, and then you evaluate it at x equals 1 to x equals t. Which I'm now going to call that guy. I think it's easier to evaluate functions with positive powers than it is to do negative powers, especially with what's about to happen in the next line. If you plug in t, you get negative 1 over 2t squared. If you plug in 1, you get negative, but you're taking that away, so I end up with plus a half. So far, so good. Now, what's going to happen to this term when t goes infinite? Well, won't brute force say it becomes 0? Because 1 over infinity is essentially 0. 0 plus a half, you get a half. So, by the integral test, the original series converges. Now here's something that I wish was true but is not. Wouldn't it be really nice if not only could I tell it converges, but it converges to a half? Wouldn't it be nice if that's what it added up to? Unfortunately, it's not. All I know is that it converges to something. And in a funny sort of a way, I know it converges to something and it's guaranteed not to be a half. It just isn't, right? The answer is that it's going to converge to something, but it'll be less than a half. Okay, you might say, well, why do I know that? Can you imagine this is what the curve looks like? Now, what you're basically doing here is creating rectangles 1 unit wide. And these rectangles are essentially, actually I just did that from the wrong side, but they're saying, look, if you do the area under the curve, if the area under the curve works, won't the area of all those rectangles also be a finite number? That's essentially what it's saying. But it doesn't guarantee that it's equal to that. Now, if the limit of this integral, right, the one we just did, if this fella was infinite, which is the other choice, right, then the conclusion would be it diverges. Now, there are techniques for finding out what does it converge to. And those techniques are numerical techniques mostly. And what they do is they will get the answer to what number it converges to whatever accuracy you want. So let's suppose somebody says, okay, I know it converges. I need to know what it converges to, and I need to know that number to 4 decimal places. Here's a very crude way of doing it. Couldn't you write a program to basically find the first 20 terms of that sequence, that series, right? Add up the first 20. And then couldn't you get it to add up the 21? And see if 2 consecutive answers rounded off are the same answer to 4 decimal places. That's the guy you're looking for. So you can imagine you just plug it into a computer and you say, okay, computer, I'm not going to spend the next 10 years of my life doing this by hand because I know you can do it in 2 seconds. Go hunting. I want the answer to 10 decimal places. Well, can you imagine the computer would just do, you know, the first million, the first million and one? Not good enough. They're only good to 3. The first billion and the first billion and one. Yep, those guys are good to 10 decimal places. Oh, there's your answer to 10 decimal places. So it's not difficult to find the numeric value for that guy. What you can't do very easily is tell me that it's pi squared over 6 or the square root of 72 or, you know, an exact value. That's not going to happen. And yeah, I guess you have to live with what you get, right? Cool test, called the integral test. You all recognize the harmonic series? Let's do an integral test on them. So I can now prove to you that that guy diverges. Up to this point, didn't I say, look, trust me, it works, it diverges, you know, trust me, blah, blah. Right, now I can prove it. Would you agree the real valued function is 1 over x? Very quickly. For x greater than or equal to 1, would you agree that's positives? If I do a derivative of this guy, can you trust me that it's that guy? And would you agree for this, it's less than 0, so it's decreasing? So I'm skipping through the conditions quickly, right? But would you agree it's definitely positive and it's decreasing? You got those 2. Now, I'm going to find the integral from 1 to infinity of 1 over x dx. So it's going to be the limit as t tends to infinity of 1 to t of 1 over x. So that becomes the limit as t tends to infinity. Okay, what's the integral of 1 over x again?
Negative 1 over x squared.
No, that's its derivative. I don't understand why you say that, but that's its derivative. What's the integral of 1 over x?
Natural log.
Yeah. Can you see in this question you do both processes, so it's easy to get them mixed up? And that's going to be evaluated at x equals 1 to x equals t. So that's going to be the limit as t tends to infinity of the natural log of t take away the natural log of 1. Okay, and brute force this. Would you agree the log of infinity is still infinite? And infinity take away 0 is infinity. That makes it diverge. So by the integral test, doesn't this guy also diverges? So 1 over n cubed converges, right? That was the first one we did, right? 1 over n cubed converges. So let's do a little family. 1 over n diverges. 1 over n cubed converges. Any bets on what 1 over n squared does? Converges or diverges? Gut feeling. Converges?
Converges.
Good. In fact, that's the last guy on the diverging side. If you want to go the other way, you have to do things with smaller powers. This entire family of functions are called P-series. P-series have one thing in common. They're always written as 1 over n to the power of something, where P could be 3, which would give you this guy. It could be 1, which gives you this guy. It could be a half, which gives you this guy. P-series have a very interesting property. If P is less than or equal to 1, the series diverges. And if it's greater than 1, the series converges. In fact, the first two examples I've given you, aren't they both P-series? 1 over n cubed is a P-series, and 1 over n is a P-series. In fact, if you want to tell someone what a P-series is, you just tell me the power. You just say, this is a P equals 3 P-series. This is a P equals 2 P-series. This is a P equals 1 P-series. And this is a P equals a half P-series. That means I can tell you, whoops, I can tell you what that P-series does. Converges or diverges. 1 over n to the power of 1.7.
Converges.
Okay. What's its p-value? You're correct. .7. Is it not bigger than 1? That's why it converges. This fella is called a P-series test. If your series is a P-series, you can tell if it converges or not by simply just telling me what the p-value is and then saying it's bigger than 1, it converges, or if it's less than 1, you will say it diverges. But, I'm going to take a pause for a few seconds and do a screen grab because I want to make sure I do it this time. We're good. Sugar and spice. Okay, it looks like I'm going to have to do 2 screen grabs, but that's fine. It's the same thing. And where are we? Oh, here we go. Now, I actually proved some of the P-series by the integral test. In fact, all the P-series can be done by the integral test. Would you agree the integral test is a lot longer than the P-series test? But the P-series is very restrictive, right? You got to look like that. Do you think putting a 10 on the top hurts or harms in any way what the answer is going to be? No. So a P-series is a basic family. Can't you have 10 on the top and it won't matter, right? Could you have a P-series like 1 over n cubed, right? Would you agree that that's P equals 3 and it converges, right? If you stuck 10 on the top, would you agree it still converges? It does what it was doing with or without the 10. Suppose you stick a 7 on the bottom. Is it still going to converge? Yes is the answer, it's still going to converge. If you do a multiple to something, right, if you make it 3 times bigger or 1/3 the size, do you know you can't affect convergence? Here's the argument. If the thing adds up to infinity, would you agree making it 10 times bigger just means it's 10 times infinity, so it's still infinite, and so it diverges? if the thing adds up to infinity, but you make it half the size that it used to be, like you stick a 2 in the bottom, isn't it going to be equal to half infinity? Oh, wait a minute, that's still infinite, so it still diverges. That's the kind of argument for why multiples top and bottom do not affect the conclusion of convergence or divergence, right? Don't matter if you stick a 10 in the top or a 4 in the bottom, as long as it's a fixed number, right? You're not allowed to stick an n on the top or an extra n in the bottom. That will change things, right? That could make things totally different, right? So let's do another integral test, moving away from our p-series. I think we've got time for this last one. Suppose I do n equals 1 to infinity, and I'd like to know n over e to the n. Do you think it might converge? Do you think it might diverge? Hard to tell. Okay. The real valued function is that guy, but I think it helps to have it written in that form. Since I'm running short of time, I'm going to skip some lines that you're not allowed to skip. Would you agree that x over e to the x is definitely positive as long as x is bigger than or equal to 1? Can you trust me that after you use the product rule to differentiate that, you end up with a mess, but that mess is negative and therefore it's decreasing? So we are left with finding the limit as t tends to infinity of 1 over t x e to the negative x dx. Do you recognize what method I'm going to have to use to integrate x e to the negative x?
Integration
Typically,
backwards.
bang on, exactly. Typically, power rule, u sub, integration by parts, right? That's going to be your 3 typical go-to guys, right? Power rule, u subs, or integration by parts. Now you do the u dv till I do the fg guy, but it ends up being the same thing, so everybody's happy. So what do I get? I get f of x, big G of x, take away the integral of f dashed x, big G of x, dx. For a little while, I'm going to ignore the 1 to t bit. So I get x e to the x, take away the integral of e to the x dx. And so I now get the limit as t tends to infinity of x, excuse me, e to the negative x. Almost missed that, which makes it plus. So we get this guy with that guy, evaluated at x equals 1 and finishes at x equals t. So that's going to be the limit as t tends to infinity. And I'm going to rewrite these as fractions. So it's going to be t over e to the t, take away 1 over e to the t, that's the first guy. Take away, what's that, 1 e to the 1, so that's 1 over e, take away, 1 over e, which is nice, 0. So I'm looking at the limit as t tends to infinity of t over e to the t, take away 1 over e to the t. And you might have hoped at this point our life would be easy, but just to show you, life isn't always easy. Let's do the easy piece. Would you agree that if you brute force it, that's going to be 0? But what about this guy? Won't we have to do some extra work to find out what its limit is? Do you recognize a good candidate for L'Hopital? So I'm going to do L'Hopital on this piece. So it's going to be the limit as t tends to infinity of 1 over e to the t, which I can now brute force. And would you agree that this guy is definitely a number? I know zeros are rather distracting number, but it is a number. And so it converges. I've got a sneaking feeling I might have missed a negative in here when I zoom through it. So that might not be 0. I've got a sneaking feeling that might be that. But whatever, right? It's still going to converge. So actually it's more likely that. But it's going to converge anyway. So you can do the details here and figure out why. I'm pretty comfortable that that's not a 0. I've got a feeling, you know, it's probably a plus. And that's a different story. Okay. What else to talk about? Oh. Have you noticed that in the integral test, I've been using the assumption that x is greater than or equal to 0. And I've used that in proving that it's positive for values of x greater than or equal to 0, and to prove that it's decreasing. And there is a little wiggle room here. According to the integral test, you only need to prove that for some fixed number a, it's true. And the reason for that is, can you imagine that some series, the first 2 or 3 terms kind of jump up and down and maybe an odd 1 or 2 is negative before it finally kind of levels off and then starts doing its thing, right? It's not that uncommon for the first couple of terms to jump around a little bit, and then it, you know, does its nice decrease to 0 kind of thing. And so you might have to say it's positive as long as x is greater than or equal to 3, and it's decreasing as long as x is greater than or equal to 3 or 4 or 5. And that's a tweak that you are allowed to do. So it doesn't need to be bigger than or equal to 1. The reason I'm saying that is I can imagine a question. Let's try and figure something else out here.